There it hangs in the blackness of space, a golden jewel crowned with shimmering rings, Saturn, the sixth planet from our Sun, and one of the most breathtaking sights in our solar system. For centuries, we've gazed up at this celestial wonder, watching it sparkle among the stars, yet even now, after decades of robotic explorers and telescopic observations, it remains a world wrapped in secrets. We've flown spacecraft through its icy rings, mapped its violent storms, and listened to its eerie radio signals. But with every answer Saturn offers, it seems to whisper 10 new questions. This is a planet that refuses to be fully known, a place where beauty and mystery exist side by side, inviting us to look closer and wonder what lies hidden in its subtle glow. And that's exactly what we're going to do today. In this video, we'll be counting down 25 of the most astonishing, mind-bending mysteries that Saturn has to offer, enigmas that challenge our understanding of science, nature, and even reality itself. From hexagonal storms larger than Earth to moons that may hide oceans of alien life, Saturn's system is a treasure trove of cosmic puzzles just waiting to be explored. Each mystery pulls us deeper into the unknown, inviting us to question what we think we know about our place in the universe and what might be possible on worlds so far from our own. So settle in, open your mind, and get ready for a journey unlike any other. We're about to dive into the heart of one of our solar system's greatest wonders, where logic sometimes falters and imagination takes flight. Whether you're new to astronomy or a seasoned stargazer, there's something here to capture your curiosity and leave you with a sense of awe. The mysteries of Saturn are calling. Let's begin. Our journey begins with one of the most visually striking and downright perplexing features in our entire solar system, a structure so precise it looks almost manufactured. High above Saturn's north pole, a colossal hexagon wider than two Earths placed side by side spins in a perfectly synchronized dance with the planet's rotation. This isn't a trick of light or shadow. It's a persistent six-sided jet stream, a geometric hurricane that has churned in the thin, gaseous atmosphere for decades, perhaps even centuries. Imagine a honeycomb pattern drawn on a planetary scale, with each side stretching over 8,000 miles and winds screaming along its edges at speeds exceeding 300 miles per hour. Yet, despite this immense violence, the shape itself remains eerily stable and unwavering, a polygon painted on the clouds that defies every conventional expectation of how fluids and gases behave. The sheer longevity of this phenomenon is a mystery in itself. We first caught glimpses of it during the Voyager flybys in the early 1980s, and when the Cassini spacecraft arrived over 2 decades later, the hexagon was still there, unchanged, a permanent fixture in Saturn's sky. This persistence is what truly baffles scientists. On a dynamic, storm-racked gas giant, where immense weather systems routinely form and dissolve, how does such an angular, delicate structure maintain its shape against the constant forces of turbulence and shear? It's like drawing a perfect square in a whirlpool and watching it hold its form for 40 years. The leading theories attempt to crack this code by looking deep below the visible cloud tops. One compelling idea suggests the hexagon is a manifestation of a standing wave pattern, a kind of stationary oscillation rooted deep in Saturn's atmosphere. Think of it like a wave frozen in time, created by differences in wind speed at various latitudes, its 6 sides locked in place by the planet's rotation. Other models point to deep atmospheric dynamics, proposing that the pattern is generated far below the clouds we can see, perhaps by some kind of convective activity or a unique interaction between different layers of Saturn's interior. Laboratory experiments here on Earth have even managed to create similar polygonal shapes by spinning fluids at different speeds, offering a tantalizing hint that the answer might lie in fundamental physics. Yet, no single theory has been able to fully replicate the stability, the precise geometry, and the sheer scale of Saturn's masterpiece. It stands as a monumental puzzle, a celestial work of art whose artist remains unknown. But the hexagon is not the only geometric marvel in Saturn's neighborhood. If we shift our gaze from the planet's pole to its magnificent rings, we encounter another transient and deeply puzzling phenomenon, one that seems to defy the very laws of orbital motion. Imagine looking at a spinning vinyl record and seeing straight, radial lines like spokes on a wheel temporarily appear across its surface, only to fade away and reappear hours later. This is precisely what happens within Saturn's B-ring, the brightest and broadest of its rings. These are the spokes, shadowy or bright features that stretch radially across the ring plane for thousands of miles, yet they are only about 100 times thinner than they are long, making them astonishingly fine and delicate structures. What makes these spokes so enigmatic is their bizarre behavior. The individual ice and rock particles that make up Saturn's rings obey the strict rules of orbital mechanics, meaning particles closer to Saturn orbit faster than those further out. This is known as Keplerian shear, and it should tear any radial structure apart within minutes. Yet, the spokes persist for hours, sometimes even multiple orbits, appearing to rotate around Saturn as a cohesive unit, as if they were painted on a solid plate. Even more strangely, they don't always rotate at the same speed as the ring particles beneath them or the planet's magnetic field above them, leaving scientists scratching their heads about what force could possibly be orchestrating this coordinated motion. Their transient and seasonal nature adds another layer to the mystery. The spokes were first documented in detail by the Voyager missions, but they virtually disappeared from view for years, only to reappear when the Cassini spacecraft arrived as Saturn approached its equinox. This suggests their formation is intimately tied to the angle of sunlight hitting the rings. The leading hypothesis points to a complex electrostatic interaction. Tiny, micron-sized dust particles, likely created by micrometeoroid impacts on the larger ring bodies, could become electrically charged by the sun's ultraviolet light or by plasma in Saturn's magnetosphere. Once charged, these tiny particles could levitate slightly above and below the ring plane, arranging themselves along the magnetic field lines that radiate out from Saturn's core. This would explain their radial, spoke-like appearance and their ability to move coherently, temporarily freed from the gravitational constraints that govern the larger ring particles. However, this elegant theory still can't fully explain the sporadic nature of the spokes or why they congregate in specific regions of the B-ring. It's a captivating celestial ballet of dust, ice, light, and magnetism, a fleeting performance on a stage millions of miles wide that we are only just beginning to understand. From the ghostly spokes that dance upon its rings, we turn to a much grander and more fundamental puzzle, one that strikes at the very heart of Saturn's identity. Where did these magnificent rings come from in the first place? We've come to think of them as a permanent fixture, an ancient crown that has always adorned the planet. But the shocking truth is that we have no definitive answer for their origin. The debate is split into two opposing camps, each with compelling evidence, and the data from the Cassini mission didn't settle the argument. It only deepened the mystery, challenging the foundations of both theories. On one side, you have the classical, romantic idea that Saturn's rings are primordial. This theory suggests they are leftover building material from the very formation of the solar system itself, over 4.5 billion years ago. In this scenario, a vast cloud of ice and rock failed to coalesce into a moon due to the immense gravitational pull of the infant Saturn, a force so powerful it shredded and sheared any budding satellite, creating a permanent, swirling disk of debris just beyond the planet's reach. It's a beautiful, elegant story that gives the rings a sense of timeless, ancient majesty, a relic from the dawn of our cosmic neighborhood. The opposing view is far more dramatic and suggests the rings are a relatively recent and violent acquisition. This theory posits that a pre-existing moon, perhaps as large as Iapetus, wandered too close to Saturn in the last few 100 million years. Caught in the planet's immense gravitational tide, this unfortunate world would have been torn apart in a catastrophic event, its icy mantle shredded into countless fragments that were then smeared into the elegant, flat disk we see today. This would make the rings a temporary spectacle, a fleeting monument to a celestial disaster that we are just fortunate enough to witness. For a long time, the young rings theory seemed to be gaining ground, primarily due to their astonishing brightness. The rings are almost pure water ice, reflecting sunlight brilliantly. Over billions of years, constant bombardment by dark, micrometeoroid dust should have gradually polluted them, darkening their appearance significantly. Their pristine, bright white sheen suggests they haven't been around long enough to accumulate much cosmic grime, pointing to an age perhaps as young as 100 million years, a mere blink in geological time, existing long after the dinosaurs vanished from Earth. But then Cassini arrived and delivered its final, monumental gift, the grand finale orbits. By diving between the rings and the planet itself, the spacecraft was able to measure the ring's mass with unprecedented precision. Mass is a critical clue to age, as heavier, more massive rings could better withstand the darkening effect of micrometeoroid pollution and could have persisted for much longer. The results were stunning. The rings were found to be even less massive than some of the most optimistic young rings models predicted. This measurement seemed to be the final nail in the coffin for the primordial theory, strongly supporting the idea of a recent cataclysmic birth. However, the mystery refused to be solved so easily. When scientists examined the chemical composition of the ring particles in exquisite detail, they found another piece of the puzzle that didn't fit. While the rings are overwhelmingly made of water ice, they also contain a subtle but significant contamination of other minerals and organic compounds. A mix of material that looks nothing like the interior of a modern icy moon. If the rings came from the destruction of a moon like Enceladus or Dione, their composition should be a much closer match. This left scientists at an impasse. The low mass points to a young age, but the peculiar contamination doesn't match the composition of any known moon that could have been destroyed. We are left with two compelling yet contradictory lines of evidence, a cosmic contradiction that keeps the true origin story of Saturn's most famous feature completely and utterly unresolved. Leaving behind the grand question of the ring's origin, our attention now turns to a much smaller, yet no less bizarre, world nestled within them. Drifting gracefully within the Inca Gap, a 300-mile-wide channel in Saturn's ring, is the moon Pan. From a distance, it appears as just another speck of rock and ice, but when the Cassini spacecraft finally gifted us with a close-up view, it revealed something that defied all expectation. Pan is not a sphere, it is not even an irregular lump. Instead, it is shaped almost exactly like a walnut, complete with a massive, razor-thin ridge that encircles its entire equator, making it look less like a moon and more like a piece of celestial poster or a flying saucer from a classic science fiction film. This equatorial ridge is not a minor feature. It is the moon's defining characteristic, a bizarre skirt of material that gives Pan its unique profile. The mystery of its formation is a puzzle of delicate balance and immense forces. How does such a massive structure form on such a small, low-gravity world without shattering it completely? For a moon with such weak gravity, the addition of so much mass around its middle should have been a catastrophic event, yet Pan holds together, a tiny, fragile world with a belt it seemingly has no business wearing. Scientists have developed two primary theories to explain this unlikely fashion statement, and both are intimately tied to Pan's very special address within the rings. The first and most widely accepted idea is the accretion model. Pan orbits snugly within the Inca Gap, but it doesn't travel alone. This path is constantly being swept clear by the moon's gravity, but it is also surrounded by an endless rain of fine ring particles. The theory suggests that over eons, this gentle snow of icy dust has been pulled down by Pan's gravity, settling along its equator, the Moon's gravitational waistline, and building up layer by layer into the colossal ridge we see today. It's a slow, gentle process of dressing a moon in the very fabric of its environment. The second theory proposes a more violent and internal origin. It suggests that Pan itself may have formed from the merger of two or even several smaller moonlets that came together in a slow-motion collision, their material piling up around a central core to create the equatorial bulge. Alternatively, some process within Pan's own structure, perhaps a past period of rapid spin, could have caused it to bulge at the middle before settling into its current form. However, these internal explanations struggle to account for the ridge's incredible symmetry and precise placement. What makes Pan's mystery even more compelling is that it is not alone. Its sibling moon, Atlas, which orbits just outside the brighter ring, shares this peculiar walnut shape. The existence of two such similarly bizarre moons in this region strongly points to a common formation process, one that is directly influenced by their unique location within Saturn's ring system. This suggests we are looking at a completely new class of celestial object, one shaped not in the emptiness of space, but within the dynamic, dusty disk of a planet's rings. Pan and Atlas stand as stunning examples of how a specific environment can craft a world into a form we never imagined possible, challenging our definitions of what a moon can be. But if you think Pan's shape is strange, just wait until we venture a bit further out from Saturn itself to one of its most captivating moons. Lurking in the cold darkness, a tiny, ice-covered world no wider than the state of Arizona is putting on one of the most spectacular shows in the entire solar system. This is Enceladus, and its south pole is the scene of a breathtaking and deeply mysterious phenomenon. A series of colossal geysers, violently erupting from deep fissures known as the tiger stripes, hurling vast plumes of water ice, organic molecules, and gas hundreds of miles into space. This isn't a gentle leakage, it's a full-blown cryovolcanic eruption, a frozen fountain that constantly replenishes one of Saturn's outermost rings and paints a picture of a world that is far from dead. The discovery of these plumes by the Cassini spacecraft completely rewrote our understanding of where life could potentially exist. Here was a moon just 300 miles across, with an estimated surface temperature near -330 degrees Fahrenheit, actively spewing out water vapor and ice particles. Subsequent flybys took Cassini directly through these plumes, and the data sent back was nothing short of revolutionary. The plumes were not just simple water. They contained a surprising brew of life's building blocks, including simple organic compounds like methane and carbon dioxide, and even more complex ones. Most astonishingly, they were salty, laden with sodium and potassium salts, and the ice grains showed a clear chemical signature that pointed to their origin. A vast, global, liquid water ocean tucked between the moon's rocky core and its icy outer shell. Enceladus, against all odds, was revealed to be a water world. This immediately presents one of the most profound mysteries in planetary science. What is the engine driving this incredible activity? For a world so small, its internal heat should have been lost to space billions of years ago, leaving it a frozen, inert ball of ice. Yet here it is, not just warm, but energetic enough to power massive jets that erupt continuously, even forming a torus of fine ice dust around Saturn. The leading theory, and the one that fits most of the data, is tidal heating. Enceladus orbits Saturn in a slightly elliptical, non-circular path, thanks to a gravitational resonance with its larger sibling moon, Dione. This uneven orbit means that as Enceladus travels, Saturn's immense gravitational pull flexes and kneads the moon's interior. This constant stretching generates friction and heat deep within, much like repeatedly bending a piece of metal will make it warm to the touch. This internal heat is what is believed to keep the subsurface ocean from freezing and provides the energy to force water up through the cracks in the ice shell at the South Pole. However, this elegant explanation is not without its own set of puzzles. The primary question is one of sufficiency and longevity. Is the amount of heat generated by this tidal flexing truly enough to maintain a liquid ocean for billions of years and power such violent eruptions? Some models suggest that the current orbital setup may not be stable over the age of the solar system, meaning this activity could be a relatively recent and temporary phase in the Moon's history. Furthermore, the heat output measured by Cassini was not evenly distributed. It was intensely concentrated at the South Pole, specifically along those 4 famous tiger stripe fractures. This extreme localization is difficult for some tidal heating models to perfectly replicate. The heat seems to be escaping in very specific, focused vents, suggesting a complex plumbing system beneath the ice that we are only beginning to fathom. This has led some scientists to speculate about additional complementary heat sources, perhaps even short-lived radioactive elements in the Moon's core providing an extra kick of warmth. The mystery, therefore, is not just about the existence of the ocean, but about the powerful, persistent, and curiously focused engine that keeps it churning, making this tiny, brilliant moon one of the most promising and puzzling places to look for life beyond Earth. But the incredible activity on Enceladus is just a prelude to an even more complex and Earth-like drama unfolding on a much larger stage. If we journey further out from Saturn, we encounter its largest moon, a world so unique it stands alone in the solar system. This is Titan, a place both hauntingly familiar and utterly alien, shrouded under a thick orange haze. Beneath that smoggy sky, Titan hosts the only other known world with a permanent liquid cycle on its surface. But here, the role of water is played by a different compound altogether, liquid methane. This moon has vast dunes, mountain ranges, and most astonishingly, rivers, lakes, and even seas of hydrocarbons, with methane rain falling from clouds in its dense atmosphere. It's a complete hydrological system, but one built from ingredients that would be a mere gas here on Earth. This leads us directly to a profound and long-standing mystery, the Titan methane cycle and its hidden source. Methane, under the relentless bombardment of ultraviolet light from the sun, does not last forever. Photochemical reactions in the upper atmosphere slowly but surely break methane molecules apart, converting them into more complex hydrocarbons like ethane and acetylene, which then rain down to the surface. Based on our current understanding of this process, all the methane in Titan's atmosphere should have been entirely depleted within a relatively short period, somewhere between tens of millions of years. Geologically speaking, that's a blink of an eye, and yet Titan's atmosphere is still about 5% methane today. Its rivers continue to flow, and its great northern seas like Kraken may remain filled. This presents an unavoidable conclusion. Titan must have a massive, hidden reservoir that is constantly replenishing the methane being lost, a source that has remained active for potentially billions of years. The central question is, what is that source and where is it hiding? Scientists have been investigating several compelling theories to solve this puzzle. The first and perhaps most dramatic idea is cryovolcanism. This theory suggests that Titan, much like Enceladus, might have a warm, liquid water ocean beneath its icy crust, laced with a significant amount of dissolved gases, including methane. Occasionally, this pressurized mixture could erupt onto the surface through cryovolcanoes, essentially spewing slushy ice and liquid methane that then evaporates to recharge the atmosphere. The Cassini mission searched intently for conclusive evidence of these icy eruptions, and while it found a handful of candidate features that might be ancient or dormant volcanoes, no smoking gun, or in this case freezing geyser, was ever definitively confirmed. A second, less flashy but equally plausible theory points to a vast subsurface reservoir. Instead of violent eruptions, methane could be slowly and steadily seeping out from the ground. Imagine a gigantic global aquifer, but one filled with liquid methane instead of water, trickling up through fractures in the moon's icy bedrock to feed the lakes and the atmosphere. This could be part of a much larger and more complex hydrocarbon groundwater system, with methane moving through porous layers of ice, much like petroleum moves through sedimentary rock on Earth. This process would be far more difficult to observe remotely, which could explain why we haven't yet found its direct signature. A third possibility delves even deeper into Titan's very core. Some models suggest that the methane could be primordial, trapped within the moon's rocky interior since its formation over 4 billion years ago, through a process called serpentinization, where water reacts with certain minerals. This ancient methane could be slowly released over eons. This would provide a steady, gentle feed of gas that percolates up to the surface, maintaining the atmospheric balance without the need for dramatic volcanic activity. Each theory has its merits, but each also faces significant challenges. The lack of definitive cryovolcanic evidence is a major hurdle for that idea. A subsurface aquifer would need to be truly immense to account for the supposed billions of years of replenishment. And a primordial source raises questions about how such a reservoir could have remained isolated and active for the entire history of the solar system. The true answer might even be a combination of these processes, a complex interplay of geology and chemistry that we are only beginning to unravel. This mystery is more than just a question of planetary science. It gets to the heart of Titan's potential for prebiotic chemistry, as this continuous cycle of methane is what drives the complex organic reactions that make this shrouded moon one of the most compelling targets in our search for the building blocks of life. Yet, even as we ponder the hidden engines that drive Titan and Enceladus, we are reminded that the planet they orbit holds a secret so fundamental we still can't answer it. How long is a day on Saturn? For a planet we have been studying for centuries, this should be a simple, basic fact. But Saturn refuses to give up this core piece of its identity, and the reason reveals just how bizarre and alien a gas giant truly is. Unlike a rocky planet like Earth or Mars, Saturn has no solid surface. There is no mountain or crater we can track as it rotates beneath the clouds. Instead, the entire visible exterior is a churning, swirling maelstrom of hydrogen and helium, with different bands of atmosphere moving at wildly different speeds, a phenomenon known as differential rotation. This means the clouds at the equator race around the planet faster than the clouds near the poles, making it impossible to define a single surface rotation period. To find the true length of Saturn's day, we need to look deeper to measure the spin of the planet's hidden interior, but that is where the mystery truly deepens. Scientists have two primary methods for probing this deep rotation, and frustratingly, they have given two different answers. The first method relies on the planet's magnetic field. Most planets, including Earth, have a magnetic field that is tilted relative to their rotation axis. This offset creates a wobble in the magnetic field as the planet spins, which can be measured by spacecraft to give a very precise rotation period. We used this technique successfully at Jupiter, but Saturn's magnetic field is almost perfectly aligned with its rotation axis. This astonishing symmetry means there is no wobble to measure. It's like trying to find the spin of a perfect sphere by looking at a dot painted directly on its north pole. From any angle, it looks the same. This bizarre lack of tilt is a profound mystery in itself, but it completely nullifies our most reliable tool for telling time on Saturn. Without a measurable magnetic wobble, scientists turn to a second method, analyzing periodic radio emissions. As Saturn rotates, its uneven magnetic field and the charged particles trapped within it are thought to generate regular, repeating signals in radio waves, creating a kind of planetary heartbeat. The Voyager missions in the 1980s used this method to establish a rotation period of 10 hours, 39 minutes, and 22.4 seconds. This was accepted as the definitive answer for decades, but when the Cassini spacecraft arrived in 2004, its more sensitive instruments detected a rhythm that had changed. The radio pulse now suggested a rotation period that was about 6 minutes longer. This was not a small discrepancy, it represented a fundamental shift. A planet's rotation rate is a fundamental property tied to its angular momentum and formation. It shouldn't just change by minutes over a couple of decades. This contradiction forced a complete re-evaluation. Was the radio signal even tied to the planet's core rotation at all? New analysis suggested these radio pulses might not be a direct heartbeat, but are instead influenced by the solar wind, fluctuating in a way that only makes them appear periodic. If that's true, then we have been listening to the wrong cosmic drummer this whole time. More recent efforts have turned to measuring incredibly subtle gravitational field anomalies or tracking the motion of stable features deep in the atmosphere. But these two have failed to provide a single, universally agreed upon number. The various measurements continue to disagree, clustering around values that differ by those crucial few minutes. This isn't just an academic debate over decimal points. The exact rotation period is the key that unlocks the true nature of Saturn's interior, the size and mass of its rocky core, the dynamics of its deep metallic hydrogen ocean, and the transfer of energy and momentum from the inside out. Without it, our models of this gas giant's very structure are built on a foundation of shifting sand, a constant reminder that for all our knowledge, some of the most basic truths about our solar system still lie just beyond our grasp. While the slow, patient ticking of Saturn's hidden clock remains a fundamental puzzle, the planet's atmosphere is anything but quiet, occasionally erupting in displays of raw power that dwarf anything our own world can produce. If you think the lightning storms on Earth are impressive, prepare to be humbled. On Saturn, atmospheric electricity operates on a truly monstrous scale, generating super bolts of lightning that release thousands of times more energy than their earthly counterparts. These aren't just brief flashes in the cloud tops. They are the heralds of the most colossal storm systems in the solar system, events so vast they can literally engulf the entire planet. The most famous and dramatic of these events are the Great White Spots. These are not merely large storms, they are global cataclysms. As the name implies, a great white spot appears as a brilliant, white, turbulent cloud complex that, once it forms, rapidly expands until it stretches around the entire circumference of Saturn. A swirling, churning belt of fury that can persist for months. What makes these storms so enigmatic is their startling predictability paired with their utterly unpredictable ferocity. They erupt with remarkable regularity, appearing like clockwork approximately once every Saturnian year, which is equal to about 30 Earth years. The last one was observed in 2010, and it was a breathtaking spectacle, a massive head of bright clouds that quickly grew to sweep around the planet. Yet, while we can predict their timing, we still don't fully understand the engine behind this incredible 3-decade-long build-up and release. The prevailing theory points to a process of immense atmospheric energy storage. For decades, Saturn's upper atmosphere acts like a giant lid, preventing warm, moist air from the interior from rising. This creates a stifling inversion layer where energy, in the form of heat and humidity, slowly and steadily accumulates. Over the course of a Saturnian year, the upper atmosphere cools just enough as the seasons change, particularly in the northern hemisphere where these spots typically form. Eventually, the stored energy becomes too great to contain. The atmospheric lid blows off, and pent-up heat from the planet's deep interior catastrophically erupts upwards in a convulsion of convection. This unleashes a plume of warm ammonia and water-rich air that punches into the cold upper atmosphere, where it condenses into those brilliant white ice crystals we see, fueling a self-sustaining storm of unbelievable proportions. But this explanation only deepens the mystery of the storm's sheer scale. Why does this process on Saturn create a single planet-encircling behemoth, while on a planet like Jupiter, which also has internal heat and convective storms, the disturbances remain as separate, swirling bands and localized great red spots. The answer likely lies in the unique vertical structure and chemistry of Saturn's atmosphere. Its deeper layers may have a much higher density of water vapor, a powerful greenhouse gas that traps immense amounts of thermal energy. When this energy is finally unleashed, the resulting convective plume is so powerful and taps into such a deep reservoir that it doesn't just create a local storm. It disrupts the entire latitudinal band of wind currents, effectively taking over the planet's weather system for a season. The lightning associated with these events is a direct result of this violent convection, as powerful updrafts and downdrafts within the storm clouds cause ice crystals and water droplets to collide, building up titanic electrical charges that discharge in radio bursts so powerful our spacecraft can detect them from millions of miles away. These storms are more than just weather. They are a fundamental planetary process, a periodic belch of Saturn's internal heat that reminds us this gas giant is a dynamic, living world, still cooling from its formation billions of years ago. Beyond the main, stately rings of Saturn lies a realm of chaos and wonder, a narrow, dynamic band of ice and dust that behaves less like a permanent structure and more like a living entity. This is the F-ring, a delicate strand less than 100 miles wide, yet it is perhaps the most active and unpredictable ring in our entire solar system. Unlike the serene, broad sheets of the A and B rings, the F-ring is a tortured, braided, and kinked ribbon, a celestial ballet of particles under the influence of gravitational forces that sculpt it in real time. Its appearance changes over days, weeks, and months, displaying channels, jets, and swirls that appear and vanish, presenting a breathtakingly dynamic puzzle. Central to this mystery are the two moons that bracket this delicate ring, named for the mythological figures who brought fire and doom to humanity, Prometheus and Pandora. These are the shepherds, their gravitational influence theoretically confining the ring particles and preventing them from spreading out into space. Pandora orbits just outside the F-ring, while Prometheus orbits just inside it. Their gravitational dance should, in theory, be predictable. As they pass by the ring, their gravity tugs on the fine material, creating the intricate patterns we observe. Prometheus, the inner shepherd, is the primary architect, its slightly elliptical orbit bringing it into a closest approach with the F-ring every 17 years or so, where it can pull out spectacular tendrils of material in its wake. But the ring's behavior consistently defies these simple predictions. The patterns are more complex, more violent, and more transient than any model can fully account for. Sometimes, Prometheus's approach creates a clean, predictable channel or a bright streamer of ice. Other times, it seems to gouge the ring, leaving behind a dark scar or triggering a chaotic explosion of material that forms temporary, bright clumps. These clumps themselves can then interact with the ring, creating secondary patterns and further disturbances. The sheer variety of structures, from tight braids to loose kinks and seemingly random jets, suggests that the gravitational nudges from the two shepherds are only part of the story. There is a deeper, more chaotic physics at play here. This has led scientists to propose the existence of a hidden cast of characters, tiny, unseen moonlets, perhaps no larger than a kilometer across, orbiting within or very near the F-ring itself. These miniature moons would be far too small to clear a gap like Pan does, but their localized gravitational influence would be more than enough to stir up the ring material as they pass through. A single small moonlet could be the culprit behind a particularly persistent kink or a strangely stable jet. It could collide with other ring material, creating a temporary burst of debris that quickly settles back into the ring, leaving only a ghostly trace for our cameras to capture. The hunt for these phantom moonlets has been ongoing, with Cassini's images occasionally revealing a candidate object, but their small size and the ring's own brightness make them incredibly elusive, like trying to spot a single swimmer in a choppy, sunlit sea from an airplane miles above. The true mystery of the F-ring, therefore, is one of chaotic interaction. It is a celestial laboratory for studying how gravity operates not in a clean, two-body system, but in a densely packed, messy environment where countless particles and multiple small moons all influence each other at once. The ring's material has a certain cohesion and resilience, a tendency to clump together due to its own weak gravity and electrostatic forces, which then fights against the shepherding moon's attempts to pull it apart. This constant tug of war between disruption and cohesion creates the ever-shifting tapestry we find so mesmerizing. It is a stark reminder that even within the seemingly clockwork precision of orbital mechanics, there exists a vibrant, unpredictable, and beautiful chaos that we are only beginning to understand. For a world so far from the Sun, Saturn exudes a surprising amount of heat. We've long understood that gas giants radiate more energy than they receive from solar radiation, a lingering warmth from the violent process of their formation billions of years ago. But when scientists began to map Saturn's upper atmosphere, they encountered a baffling temperature anomaly that defies all conventional models. The upper layers of the gas giant are hot hundreds of degrees hotter than they should be based solely on its distance from the Sun or its internal heat flow. This isn't a slight miscalculation, it's a major discrepancy, and it points to a powerful, hidden engine pumping energy into the upper skies. Even more curiously, this heat isn't distributed evenly. The poles, those regions that receive the least amount of sunlight, are actually the hottest places of all, blazing with temperatures far exceeding those found at the equator. This bizarre reversal of expectations suggests that the familiar rules of atmospheric heating simply don't apply here, forcing us to consider far more exotic and dynamic processes at work. The most compelling suspect in this thermal mystery is one of the most spectacular light shows in the solar system, Saturn's intense and constant auroras. Much like Earth's northern and southern lights, these dazzling displays are created when charged particles from the solar wind are funneled by the planet's magnetic field down into the upper atmosphere near the poles. There, they collide with gas molecules, causing them to glow in ethereal hues. But this process doesn't just create light, it also generates a tremendous amount of heat through electrical currents and atmospheric friction. For decades, scientists theorized that these auroral ovens could be the primary source of the unexplained polar heat, but a major problem remained. How does that intense thermal energy, generated at the very top of the atmosphere around the poles, get distributed planet-wide to explain the overall warmth of the upper layers? The poles are hot, but the equator is still unexpectedly warm, and a simple diffusion of heat across such vast distances seemed too slow and inefficient to account for the global phenomenon we observe. The Cassini mission provided the crucial data needed to crack this case, revealing a mechanism far more elegant and powerful than anyone had imagined. The spacecraft's instruments detected a series of enormous, planet-sized wind systems flowing from the poles down to the equator, acting as a massive planetary heat distribution network. Think of it as a global scale weather pattern, a conveyor belt of warm air. The incredible energy input from the auroras doesn't just heat the immediate area, it sets the entire upper atmosphere in motion. This creates a colossal system of circulation where hot gas, superheated at the poles by the constant auroral bombardment, is then pushed by powerful winds toward the equator over a period of years. As this air travels, it gradually cools, but not before it has raised the temperature of the entire upper atmospheric blanket. This process effectively smears the intense polar heat across the face of the planet, solving the puzzle of the global temperature anomaly. However, this elegant explanation only deepens another layer of the mystery. While the auroral heating model works beautifully for Saturn's south pole, the North Pole presented a confounding contradiction. During the early years of the Cassini mission, the northern hemisphere was emerging from its long winter and was shrouded in darkness. Yet, despite the lack of sunlight and before the auroras there had fully ignited, the North Pole was already just as hot as its southern counterpart. This discovery was a major surprise. It suggested that while auroras are undoubtedly a primary driver, they cannot be the only source of this immense energy. There must be an additional, supplemental heat source contributing to this phenomenon, something that operates independently of the dazzling light shows. This has led scientists to probe even deeper, looking for answers within Saturn itself. One provocative theory points to the planet's immense internal heat, a remnant from its formation. The question is how that deep-seated warmth could possibly travel upwards to affect the outermost layers of the atmosphere. Some models suggest that Saturn's weather might be far more efficient at transporting this internal energy vertically than we previously thought, perhaps through large-scale atmospheric waves or other convective processes that we have yet to fully understand. Another, more recent hypothesis involves a different kind of energy altogether, the planet's own gravity waves. As energy moves through the deep atmosphere, it could generate waves that propagate upwards, much like waves crashing on a beach. When these waves break in the thin upper atmosphere, they would release their energy as heat, providing a continuous planet-wide warming effect from the inside out. This could be the secondary heater that keeps the poles warm even when auroral activity is low, a constant internal drumbeat of energy that complements the intermittent fury of the solar wind. The true answer likely involves a complex cocktail of all these processes: auroral heating, internal heat redistribution, and atmospheric wave dynamics working in concert to create an atmospheric enigma that continues to challenge our fundamental understanding of how planetary climates function. And yet, for all the dynamic processes that seem to govern Titan's surface and skies, this moon holds a chemical conundrum that strikes at the very heart of our understanding of its complex environment. We've established that the methane in the atmosphere is constantly being broken apart by sunlight, creating a cascade of more complex hydrocarbons. The primary, most stable end product of this cosmic chemistry set should be ethane. In fact, based on the estimated rate of methane destruction over Titan's multi-billion-year history, scientists confidently predicted that this process should have generated a staggering quantity of ethane, enough to create a global ocean of the stuff hundreds of meters deep, completely covering the entire moon in a sludge of liquid hydrocarbons. But when we actually looked, the numbers didn't add up. The amount of ethane actually detected in Titan's atmosphere is a mere fraction of what the models insist should be there. It's as if we've carefully tracked all the ingredients going into a factory and calculated the expected output, only to find the warehouse almost empty. So, if the ethane isn't accumulating in the atmosphere as a gas, and it's not covering the surface in a global ocean, where in the world did it all go? This missing ethane presents a first-class chemical mystery, and solving it requires us to become cosmic detectives, searching for a hidden sink that's been quietly mopping up this compound for eons. The most straightforward theory is that the ethane is simply hiding in plain sight, pooled on the surface. We know Titan has vast lakes and seas in its polar regions, and while the largest ones like Kraken Mare are predominantly methane, many of the smaller lakes and deeper parts of the seas are believed to be rich in ethane. This heavier hydrocarbon, less volatile than methane, would naturally settle and accumulate in these cold traps. The problem with this idea is one of volume. Even if we account for all the known liquid bodies on Titan, they still don't come close to holding the immense quantity of ethane that should have been produced over geological time. It's a good start, but it's like trying to explain a missing ocean by pointing to a few large lakes. The scale is just fundamentally wrong. This has led scientists to propose more inventive and permanent solutions. Perhaps the ethane isn't just pooled, it's percolating. One compelling idea is that liquid ethane from the surface is slowly seeping down through the porous water-ice bedrock, effectively draining into a gigantic subterranean aquifer. This would create a massive hidden reservoir of liquid hydrocarbons, a second, deeper ocean beneath the icy surface that we cannot directly see. This theory is especially attractive because it could also help solve the mystery of the missing methane source. Such a reservoir could be exchanging material with the surface lakes and the atmosphere in a complex cycle we're only beginning to model. Another possibility moves from geology to chemistry, suggesting that the ethane isn't being stored at all, but is instead being destroyed or converted into something else. On Titan's cold surface, ethane is a liquid, and it could be reacting with other compounds to form entirely new materials. For instance, it might be getting incorporated into the thick, organic, rich dunes that blanket Titan's equator. These dunes are made of complex, tar-like substances called tholins. Ethane could be a key ingredient in their formation, essentially getting locked away in a solid, plastic state. An even more exotic theory involves a process called clathrate hydration. If liquid ethane comes into contact with water ice at the right temperature and pressure, it can become trapped within a crystalline cage of water molecules, forming a solid structure called a clathrate. This process would effectively remove ethane from the active cycle, burying it within the moon's icy crust. Each of these theories offers a plausible hiding place, but they all come with their own set of challenges, and the true answer may involve a combination of all these processes, a complex, multi-stage filtration system that has been quietly operating on Titan for billions of years, permanently archiving the products of its atmospheric chemistry. Leaving behind the dynamic chaos of the F-ring, we now set our sights on one of the most distant and bizarre members of Saturn's family, a moon that looks less like a natural satellite and more like a celestial yin-yang symbol spinning through the void. This is Iapetus, a world of stunning and inexplicable contrasts. Its most famous feature is a color dichotomy so absolute it seems almost impossible. One hemisphere is as bright and reflective as freshly fallen snow, while the opposite side is darker than charcoal, a stained landscape that absorbs nearly all the sunlight that hits it. This isn't a gentle gradient, it's a sharp, dramatic line separating night from day on a single globe. But as if this two-tone mystery weren't enough, Iapetus has another, even more jaw-dropping feature. A monstrous equatorial ridge that runs perfectly along its middle, a continuous mountain chain that circles the entire moon, making it look like a colossal walnut or a real-world Death Star. The mystery of the coloring is a classic chicken and egg problem that has divided planetary scientists for decades. The leading theory for the dark material is external deposition. Iapetus has a peculiar, locked orbit, meaning the same hemisphere always leads the moon in its path around Saturn, like a front bumper constantly plowing through space. The theory suggests that this leading hemisphere has been bombarded for eons by dark dust, likely flung off from a distant, irregular source. The prime suspect is Phoebe, a dark, captured moon orbiting far beyond Iapetus. Micrometeoroid impacts on Phoebe's surface could be kicking up a vast ring of fine, dark particles that slowly spiral inward toward Saturn. Iapetus, on its steadfast journey, would then sweep up this cosmic soot, painting its face black. This theory is elegant and has supporting evidence. The Cassini spacecraft did indeed find a faint, massive ring of material in Phoebe's orbit, lending credence to the idea of an external paint job. However, the plot thickens with the concept of thermal segregation. This process suggests the dark coating isn't just a passive layer of dust, it's an active agent of change. The dark material, being soot-like, absorbs sunlight much more efficiently than the bright water ice beneath it. As the leading hemisphere gets coated, it begins to warm up. Even a slight increase in temperature on an airless world is enough to trigger a powerful positive feedback loop. The warmer temperature causes any embedded water ice on the dark side to sublimate, to turn directly from a solid into a gas. This water vapor then travels across the moon and refreezes onto the colder, brighter areas, particularly the poles and the trailing hemisphere. This process effectively cleans the dark areas, making them even darker and more absorbent, while painting the bright areas even whiter with a fresh layer of pristine frost. The two-toned appearance, therefore, becomes self-perpetuating and increasingly extreme over time. But while the dust deposition and thermal segregation models beautifully explain the coloring, they completely fail to account for the Moon's other monstrous feature, the equatorial ridge. This is not a small hill. It is a continuous, jagged wall of ice and rock that stretches over 800 miles long, reaching heights of 12 miles in some places and widths of up to 12 miles across. For a moon only 900 miles in diameter, this is a tectonic feature on a scale that defies all logic. It is so precise and so symmetrical that it looks artificial, a perfect seam running around the moon's waist. No other moon in the solar system has anything remotely like it. The theories for the ridge's formation are just as dramatic as the structure itself. One of the most compelling ideas is that Iapetus had a much faster spin rate in its distant past. As it cooled and its internal structure settled, the moon would have contracted, shrinking like a drying apple. If it was spinning rapidly enough, this contraction could have focused immense stress along the equator, causing the crust to crumple and buckle upwards into a single massive ridge. Another, even more spectacular theory proposes that the ridge is the remnants of a ring system that Iapetus itself once possessed. In this scenario, a massive impact early in the moon's history could have blasted material into orbit, forming a temporary ring. Over time, this ring would have destabilized and collapsed back down onto the moon. But because of Iapetus's unique gravitational field, the debris would have been funneled to crash down directly along the equator, piling up to form the immense ridge we see today. Yet herein lies the central, frustrating Chinese letter of Iapetus. The processes that best explain the two-tone coloring and the processes that best explain the equatorial ridge seem to be completely independent of one another, and no single model has yet managed to successfully link these two utterly unique features into one cohesive history. It is as if this distant moon is the product of two separate, catastrophic events that happen to occur on the same tiny world, a cosmic coincidence that challenges our desire for simple, elegant explanations. Iapetus stands as a stark reminder that nature is often more complex and more creative than our models can predict. A black and white enigma wrapped in a mountainous ridge, silently orbiting at the very edge of our understanding. Deep within the majestic, sunlit expanse of Saturn's ring, far from the chaotic braiding of the F-ring, exists a far more subtle and intriguing class of celestial object. These are not moons in the traditional sense, but something far more elusive, the propeller features. From a distance, they appear as delicate, S-shaped wisps or scars etched into the brilliant sheet of ice, each one a tiny, double-lobed disturbance stretching barely 30 miles across. But these faint markings are the ghostly signatures of an entirely new class of moon, one that has never been directly seen. Each propeller is created by the gravitational influence of a tiny, unseen moonlet, likely no larger than a kilometer across, embedded within the ring itself. These hidden worlds are too small to possess the gravitational muscle to clear a full gap like their larger cousin Pan, but they are just large enough to pull and tug on the ring particles immediately around them, creating a distinctive shape that looks remarkably like a vintage airplane propeller spinning in the ice. The very existence of these features forces us to rethink the architecture of planetary rings. We once imagined the rings as a relatively simple, flat disk of particles sorted by size and density, with only a handful of larger moons acting as shepherds or sculptors. The propellers reveal a much more complex and crowded ecosystem, one teeming with countless unseen, kilometer-sized objects that are effectively the boulders of the ring system. They are the missing link between the tiny, dust-sized particles and the massive, gap-clearing moons, a population of intermediate-sized bodies that had been theorized but never before confirmed. The Cassini spacecraft didn't just spot a few of these features, it discovered thousands of them, each one a flag marking the presence of a hidden world. They were even given informal names like Blériot after a pioneering aviator, marking them as permanent, if fleeting, residents of this dynamic environment. But as with so many of Saturn's puzzles, the reality of the propellers turned out to be far stranger than their initial discovery suggested. The central mystery is not their existence, but their peculiar and unexpected behavior. According to our fundamental understanding of orbital mechanics, these small moonlets should be locked into a predictable dance. As they interact gravitationally with the ring particles, they should experience a constant, gentle drag, a force that should slowly but surely cause them to migrate inward, drifting inexorably closer to Saturn over time. This process, known as tidal migration, is a standard and well-modeled phenomenon. Yet, when scientists tracked the propellers over years of Cassini observations, they found something astonishing. Many of them were not drifting inward as predicted. Some appeared to be completely stationary, holding their position against the relentless pull of physics, while others seemed to be migrating at rates that were completely unpredictable and inconsistent from one propeller to the next. This defiance of gravitational expectation points to forces at work that we are only beginning to understand. The leading hypothesis suggests that the propeller moonlets are not isolated objects, but are instead engaged in a complex gravitational dialogue with much larger moons far outside the rings, like the massive moon Mimas. The gravity of these distant but powerful moons could be creating resonant locations within the ring, specific orbital distances where the gentle nudges from afar act to trap and hold the tiny moonlets in place, effectively preventing their inward migration. It's a delicate balancing act where the pull of a giant moon hundreds of thousands of miles away counteracts the local drag from the ring particles, creating stable points where these tiny objects can park themselves for what might be millions of years. Another possibility is that the propellers themselves are not what they seem. Perhaps they are not solid, singular moonlets at all, but are instead loose, transient clumps of material that periodically form and dissolve. In this scenario, what we identify as a persistent propeller might actually be a series of different clumps appearing in roughly the same location, giving the illusion of a single, stable object. Alternatively, the shape and behavior of the propeller might be influenced by the collective gravity of the ring particles themselves, a phenomenon known as self-gravity wakes, which could alter how the central moonlet interacts with its environment and migrates through it. The true answer likely involves a combination of these factors: resonant pinning, clumpy composition, and collective effects, all working together to create a system of delicate, S-shaped enigmas that challenge our most basic assumptions about how objects move and interact within a disk of debris. They are a testament to the hidden complexity lurking within what appears to be a simple, serene plane of ice, a reminder that even in the most ordered-looking systems, there are always deeper layers of mystery waiting to be unraveled. But if you thought the challenge of measuring Saturn's day was a puzzle of silence and missing wobbles, prepare for a story that adds a layer of pure contradiction. For decades, we've been listening to the planet, and it has been singing to us a powerful, rhythmic song broadcast in radio waves across the solar system. This is Saturn kilometric radiation, or SKR, a natural radio emission generated by energetic particles spiraling along the planet's magnetic field lines. At Jupiter, the same kind of radio pulse is as reliable as a metronome, perfectly synchronized with the rotation of the planet's solid core and giving us a precise length for the Jovian day. So naturally, when the Voyager spacecraft first detected a similar, repeating radio pulse from Saturn, we thought we had finally found the planet's true heartbeat, a signal that would cut through the atmospheric noise and give us a definitive rotation period of 10 hours, 39 minutes, and 22.4 seconds. This number was etched into textbooks for over 20 years, accepted as a fundamental fact about the ringed planet. The arrival of the Cassini spacecraft in 2004, however, revealed this cosmic rhythm to be utterly untrustworthy. Cassini's more sensitive ears detected a profound shift. The radio pulse had slowed down. The planet's heartbeat was now indicating a rotation period that was a full 6 minutes longer. A planet's rotation, tied to its fundamental angular momentum, simply cannot change that dramatically in a matter of decades. This was impossible. It meant that the radio emissions could not be a direct, unerring signal from the planet's deep interior as they are at Jupiter. Instead, they were something else entirely, a signal that was influenced, modulated, and ultimately corrupted by external forces, creating the illusion of a changing rotation rate. The search for the true conductor of this cosmic orchestra led scientists to a powerful external candidate, the solar wind. This constant stream of charged particles flowing from the sun doesn't just cause auroras, it also presses against Saturn's magnetic field, compressing it on the sun-facing side and stretching it out into a long magnetotail on the other. This constant buffeting appears to have a direct and dramatic impact on the intensity of the SKR. During periods of heightened solar activity, when the solar wind is strong, the radio emissions can become more powerful and more frequent. The theory suggests that the solar wind's pressure might actually be able to strip plasma away from Saturn's magnetosphere, and this loss of material could subtly alter the currents flowing within the magnetic field, which in turn modulates the radio bursts we detect. It's as if a strong wind is not just shaking the leaves on a tree, but is actually changing the tree's fundamental resonance. This explanation, however, only deepens the mystery of why Saturn's radio emissions are so uniquely susceptible to this interference while Jupiter's remain steadfast. The answer likely lies in that other great mystery, the perplexing alignment of Saturn's magnetic field. Because the field is almost perfectly symmetric, with its north and south magnetic poles almost exactly coinciding with its rotational poles, it may lack the stability of Jupiter's tilted field. A tilted magnetic field might act like a gyroscope, maintaining a stable rotation, whereas Saturn's symmetric field might be far more easily pushed and pulled by external forces like the solar wind, causing the sources of the radio emissions to drift around the planet and creating the illusion of a changing rotation period. Furthermore, Cassini's long mission revealed another bizarre twist. The northern and southern hemispheres of Saturn were actually broadcasting their own separate radio songs at slightly different frequencies, and these rhythms changed over time, even occasionally swapping their rates. This proved that the SKR was not a single, unified signal from the core but a complex atmospheric phenomenon, likely tied to long-lived weather systems or other sources of convection in the polar upper atmosphere that were themselves drifting at different speeds. The final, frustrating conclusion is that Saturn kilometric radiation is not the planet's heartbeat after all. It is the sound of its dynamic and ever-changing magnetosphere breathing in and out with the solar wind, a fascinating cosmic signal that has, ironically, become the primary source of our confusion about one of the most basic facts of the planet we seek to understand. Yet, even as we decode the complex radio whispers of Saturn itself, one of its most distant moons tells a story not through sound, but through a shape so bizarre it defies simple explanation. Journey out beyond the realm of the ring shepherds and the two-toned Iapetus, and you will find Hyperion, a world that looks less like a celestial body and more like a colossal piece of cosmic coral or a pumice stone hurled through space. This moon is a true oddity, a spongy, crater-riddled anomaly that behaves in a way completely unlike any other known moon in our solar system. Its most defining characteristic is its staggering porosity. It is not a solid ball of rock and ice, but a fragile, open framework, with as much as 40% of its volume being nothing but empty space. If you could squeeze Hyperion together, removing all its gaps, it would collapse into an object less than half its current size. This incredible fluffiness gives it a density so low that it would likely float if you could find an ocean large enough to put it in. This bizarre structure is written across its entire surface, which is a nightmare landscape of deep, dark pits and sharp, jagged ridges. The craters on Hyperion are not like the bowl-shaped impressions we see on most moons. They are deep, cylindrical wells with dark material gathered at their bottoms, giving the entire moon the appearance of a giant wasp's nest or a kitchen sponge magnified to a 200-mile diameter. This strange anatomy points directly to a violent and peculiar history. The prevailing theory for its formation is one of catastrophic disruption. Scientists believe that Hyperion may be the largest remaining fragment of a much larger, ancient moon that was shattered in a colossal impact event billions of years ago. Instead of the debris re-accreting into a solid body, the fragments merely gathered together in a loose pile, held by their mutual gravity but never fully compressing into a denser object. This created a rubble pile moon, a collection of icy blocks with vast gaps in between, forever preserving the evidence of its violent birth. But Hyperion's mysteries don't end with its static structure. They extend into its motion, which is just as chaotic and unpredictable as its appearance. While almost every other sizable moon in the solar system has settled into a graceful, synchronous rotation, keeping one face permanently pointed toward its parent planet, Hyperion tumbles. Its rotation is completely chaotic, meaning its axis of spin wobbles so wildly that it is effectively impossible to predict which part of the moon will be facing Saturn or the Sun from one month to the next. There is no pattern, no rhythm. It is a celestial drifter, flipping and turning erratically as it travels along its orbit. This chaotic tumble is a direct consequence of its irregular shape and its orbital dance with the much larger moon Titan. Hyperion's elongated, potato-like form makes it highly susceptible to gravitational torques. Furthermore, it is locked in a gravitational resonance with Titan, meaning the two moons periodically pass each other in a consistent, repeating ratio of orbital periods. Specifically, for every 3 times Titan orbits Saturn, Hyperion orbits exactly 4 times. This resonant gravitational nudging, combined with Hyperion's highly non-spherical shape, continuously perturbs the moon, preventing it from ever settling down into a stable, synchronous spin. It's like trying to balance a pencil on its point on a constantly vibrating table. The slightest influence sends it into a new, unpredictable rotation. This makes Hyperion one of the very few objects in the solar system known to exhibit such chaotic rotation, a dynamic state that is incredibly difficult to achieve and maintain. It is a perfect example of celestial mechanics in its most raw and unrestrained form, a world whose very motion is a testament to the violent and disruptive forces that shaped it long ago. While we often think of Titan's hydrocarbon cycle as a slow, steady process, its atmosphere is actually a stage for some of the most dramatic and unpredictable seasonal changes observed on any world in our solar system. Saturn's long orbit, taking nearly 30 Earth years to complete, means each season on its largest moon lasts for over 7 years. This extended timeline allows for colossal atmospheric shifts to develop, unfold, and then vanish, creating a slow-motion weather drama that we have only just begun to witness in its entirety. The Cassini spacecraft provided our first continuous look at this spectacle, and what it revealed was a system of breathtaking complexity that operates on a scale and with an intensity that continues to defy our best predictive models. One of the most visually stunning manifestations of these seasons is the formation and disappearance of immense cloud systems. As the long Teutonian winter grips the North Pole, the atmosphere there grows incredibly cold. This triggers a massive sinking of dense, hydrocarbon-rich air, creating a high-pressure system that suppresses cloud formation. All the while, this cold air is slowly building up a reservoir of methane and other volatiles. Then, as the spring equinox approaches and sunlight returns to the north, this pent-up energy is released in a spectacular outburst of convection. Enormous, continent-sized clouds of methane begin to erupt at the North Pole, heralding the change of season. These aren't gentle wisps, they are powerful storm systems that can unleash torrential rains of liquid methane, filling the northern lakes and seas. The models predicted this general pattern, but the sheer size, persistence, and ferocity of these springtime cloud outbreaks have been a major surprise, suggesting there are far more powerful forces at work deep within the atmospheric circulation than we currently understand. Perhaps the most puzzling seasonal event occurred at the opposite pole, just as the South was plunging into its own autumn darkness. Cassini's cameras observed a sudden and spectacular development high above the South Pole, the rapid formation of a vast, swirling vortex of haze and gas. This wasn't a simple storm. It was a permanent-looking, hurricane-like structure anchored directly over the pole, complete with a bizarre hood of elevated haze particles that made it look like a giant, upside-down wedding cake suspended in the sky. The vortex itself was a maelstrom of gases spinning at impressive speeds, but the real mystery was its composition and its temperature. This polar vortex became an intense cold spot, far colder than any other part of the Moon's upper atmosphere. This extreme chill was the catalyst for a mysterious chemical process. Within the vortex, gases that are normally inert at Titan's balmier temperatures began to condense out, forming entirely new and exotic types of ice crystals from compounds like hydrogen cyanide and benzene. This presented a profound enigma. While we see polar vortices on other planets, including Earth, Titan's version behaved in ways that are completely unique. The depth of the cold and the speed at which these complex ices formed was unprecedented. Current atmospheric models struggle to account for how such a concentrated and persistent cold trap could form so quickly. The leading idea suggests that as the South Pole entered darkness, the lack of sunlight caused the air there to cool and sink rapidly. But the intensity of this sinking and the way it became isolated from the warmer equatorial regions seems to have been far more efficient than anyone predicted. It's as if the atmosphere above the South Pole developed a kind of insulation, allowing it to become radically colder than its surroundings and triggering a cascade of chemical reactions we are only beginning to identify. The vortex stands as a stark reminder that Titan's atmospheric chemistry is not a slow, gentle process but can be catapulted into hyperdrive by seasonal changes, creating conditions in a single localized area that are utterly alien to the rest of the Moon. Underpinning all of these visible changes is an even grander and more elusive mystery: the complete reversal of Titan's global atmospheric circulation patterns with the turning of the seasons. On Earth, our weather is driven primarily by the temperature difference between the equator and the poles. On Titan, with its slower rotation and much longer seasons, the driver is the extreme temperature difference between the hemisphere in sunlight and the hemisphere in darkness. For decades during the long winter, the atmospheric engine is single-celled. Dense, cold air sinks over the winter pole, flows along the surface toward the warmer summer hemisphere, rises there, and then travels back at high altitude to complete the loop. This massive planet-encircling cell dominates Titan's climate for years, but around the equinox, when both poles receive equal sunlight, this system doesn't just weaken, it undergoes a catastrophic and rapid breakdown. The single, stable cell collapses and is replaced by two opposing cells, a complete reversal of the atmospheric engine that can happen in a surprisingly short amount of time. This flip is theorized to be the trigger for the massive cloud outbreaks and the formation of the polar vortices. However, the speed and the violence of this transition have been difficult to model accurately. The atmosphere appears to be far more dynamic and turbulent during these periods of change than our simulations can replicate, with waves and eddies transporting heat and chemicals in unexpected ways. The true mystery of Titan's seasons is not just the individual events we can see, but the hidden, global-scale machinery of its atmosphere that operates on a level of complexity rivaling our own planet's, all governed by a set of rules we are still struggling to decode. And now we turn from the dynamic, hazy skies of Titan to a moon that, for centuries, appeared to be little more than a quiet, frozen relic of the past. Dione, the fourth largest of Saturn's moons, presents a facade of serene, cratered stillness. Its surface is a pale landscape of water ice, scarred by the evidence of ancient bombardments, seemingly a world that has been geologically dead for billions of years. But as is so often the case in Saturn's system, first impressions are profoundly deceptive. Glimpsed by the Voyager probes as little more than a speck of light, Dione held a secret that only the superior eyes of the Cassini spacecraft could reveal. Vast, complex networks of brilliant, wispy lines crisscrossing its trailing hemisphere, tracing across the craters and plains like ethereal, frozen lightning bolts. These striking features, initially a complete puzzle, became the first clue in a profound re-evaluation of this quiet moon, suggesting that deep beneath its icy crust, a global ocean of liquid water might be stirring, placing Dione in the esteemed and surprising company of moons like Enceladus as a potential haven for life. The mystery of the wispy terrain begins with its simple yet baffling appearance. From a distance, these features look like bright, reflective scars painted onto the darker, older ice. Cassini's close-up views revealed their true nature. They are not mere discolorations, but enormous cliffs of exposed, clean ice. These are tectonic fractures hundreds of miles long, where the moon's brittle outer shell has been cracked open like an egg. As fault lines opened, perhaps due to global tectonic stresses, bright, fresh ice from Dione's interior was revealed along the cliff faces, while darker materials slid down into the valleys between them, creating the stunning contrast we see from orbit. This immediately presented a profound question. What powerful force could be cracking open a moon that is only 600 miles wide, a world we assumed had lost its internal heat eons ago? Geological activity on this scale requires a potent engine, and for a moon of Dione's size, that engine should have run out of fuel long ago. The answer, as with Enceladus, appears to be tidal heating. Dione is locked in a gravitational dance not with just one, but with two other moons. Its orbital period is exactly twice that of the smaller, but closer, moon Enceladus, and it is also in a resonance with the massive, distant Titan. This intricate choreography means that with every orbit, Dione receives a consistent gravitational squeeze from Saturn, its path stretched and relaxed in a regular rhythm. This constant flexing generates friction deep within the moon's interior, producing enough heat to potentially maintain a layer of liquid water between its rocky core and its solid icy shell, a global subsurface ocean. The stresses from this flexing are the most likely culprit for the massive tectonic cracking that created the wispy terrain, a visible symptom of the dynamic forces churning within. However, Dione's story is not a simple copy of Enceladus's, and here the mystery deepens in a compelling way. Enceladus, with its spectacular south polar geysers, is a moon that proudly displays its inner ocean to the universe, violently venting its contents into space. Dione, by contrast, is the quiet, reserved sibling. While scientists have detected a tenuous oxygen atmosphere around Dione and faint particle fluctuations that hint at possible, incredibly weak venting, it shows nothing like the dramatic plumes of its smaller neighbor. This presents a fascinating planetary puzzle. Why would two moons, both theoretically undergoing tidal heating, express their internal oceans in such dramatically different ways? The answer likely lies in the thickness of their icy shells. Enceladus has a thin, fractured shell at its south pole, allowing its ocean easy access to the surface. Dione's icy crust, on the other hand, is believed to be many times thicker, perhaps dozens of miles deep. This formidable frozen barrier would effectively seal the ocean in, preventing massive eruptions but allowing the built-up internal pressures to crack the surface on a global scale, creating the wispy fractures as a subtle yet monumental release valve. This distinction makes Dione a critical puzzle piece in our understanding of ocean worlds. It represents a different evolutionary path, a moon that may harbor a vast, ancient sea but keeps it hidden under a thick, frozen lid. The presence of a subsurface ocean on Dione, while strongly supported by gravity measurements from Cassini, is not yet as definitively proven as it is on Enceladus, leaving room for vigorous scientific debate. Some models suggest that the Moon's interior could be warm enough for a layer of soft, convecting ice rather than a full-fledged liquid ocean, which could also generate the tectonic stresses needed for the wispy terrain. The true nature of Dione's interior remains one of the most enticing unresolved questions at Saturn, a mystery that beckons future missions to listen for the slosh of its hidden waters and understand why this quiet, fractured world chose to keep its secrets so much closer to its chest. But the dynamic interactions between Saturn and its rings extend far beyond the visible drama of shepherds and propellers, revealing a far more subtle and insidious process that is slowly eroding the planet's most iconic feature. For decades, we viewed the rings as a stable, almost permanent adornment, but we now know they are under constant assault from their own parent planet in a phenomenon known as ring rain. This isn't a metaphor, it is a literal, ongoing shower of tiny ice particles and dust that is steadily draining material from the rings and funneling it down into Saturn's upper atmosphere. The discovery of this process fundamentally changed our perception of the rings from a static museum piece to a dynamic, evolving system with a potentially limited lifespan. The mechanics behind this cosmic drizzle are a fascinating interplay of forces. It begins with the relentless bombardment of the rings by micrometeoroids and solar ultraviolet radiation. These impacts and energy bursts charge the tiny, dust-sized ice particles, giving them a slight electrical charge. Once electrified, these particles become susceptible to the invisible lines of force that make up Saturn's immense magnetic field. The planet's magnetic field doesn't just create auroras, it also acts like a vast network of celestial highways, guiding these charged particles along specific paths. For a significant portion of this material, the path does not lead to another part of the ring system, but rather curves inward, dragging the particles down magnetic field lines that connect directly to the planet's atmosphere. As they fall, they accelerate, eventually striking the upper layers of Saturn's gaseous envelope at tremendous speeds, where they vaporize and become incorporated into the atmosphere itself. This process was first hinted at by Voyager data, which detected strange dark bands in Saturn's upper atmosphere that seemed to correlate with gaps in the rings. But it was the Cassini mission that delivered conclusive proof during its final, daring grand finale orbits. As the spacecraft dove between the rings and the planet, its instruments were peppered with a surprisingly large amount of material falling in from the rings. They detected not just water ice, but a complex cocktail of ring particles, including organic compounds like butane and propane, all raining down into the planet. This proved that the rings are not isolated. They are in a constant, intimate chemical exchange with Saturn itself. The implications of ring rain are staggering, primarily for the ring's longevity. The rate of this material loss is not trivial. Current estimates suggest this draining process could completely strip the rings of their substance within a few 100 million years, a mere fraction of the solar system's age. This timeline provides powerful evidence for the young rings hypothesis, suggesting they are a relatively recent addition to Saturn's system rather than a primordial fixture. However, this also presents a new puzzle. If the rings are this ephemeral, and if they are being depleted so rapidly, what mechanism could have created such a massive and bright structure so recently in cosmic history? The ring rain phenomenon doesn't just answer a question, it deepens the mystery of the ring's ultimate origin. Perhaps the most perplexing aspect of ring rain is its strange selectivity. The influx of material is not uniform across Saturn's latitudes. Instead, it falls in distinct dark bands that correspond to specific magnetic field lines connected to particular parts of the ring system. This creates a bizarre and beautiful map of influence, where the planet's atmosphere is being chemically altered in very specific zones by the constant drizzle from its rings. The composition of the rain itself is also a mystery. Cassini detected a much higher abundance of certain molecules, like nanograins of silicates and complex organics, than expected. This suggests that the process of charging and transporting the particles is somehow filtering them, favoring certain sizes and compositions over others in a way that scientists do not yet fully understand. This intricate, invisible connection between the ring's composition, the planet's magnetic field geometry, and the chemistry of its atmosphere represents one of the most complex and poorly understood relationships in the entire Saturnian system. A silent, slow-motion waterfall that is gradually washing away a celestial wonder right before our eyes. Yet, even as we contemplate the slow, cosmic rain that is eroding Saturn's grandest feature, we find a tiny world where the evidence of any such bombardment seems to have been mysteriously erased. Journey inward past the dynamic F-ring and closer to the planet itself, and you will find a collection of minuscule moons orbiting within the very faintest and most tenuous of Saturn's rings, the G-ring. Among these tiny specks is a world called Methone, a moon so small you could walk its entire circumference in less than a day. From a distance, it appears as little more than a speck of dust, but when the Cassini spacecraft turned its powerful cameras toward it, it revealed something that defied all logic for a body of its size. Methone is not a rough, cratered asteroid-like object. It is not a collection of rubble. Instead, it possesses an almost impossibly smooth, egg-shaped surface, a celestial ovoid that looks as if it has been polished by some cosmic hand. Its surface is so uniform and so devoid of the familiar pockmarks of impact craters that it stands completely alone in the solar system, a gleaming anomaly that challenges our most basic assumptions about how small worlds evolve. For any object in space, a lack of impact craters is a clear sign of a young surface or a recent planet-wide resurfacing event. On large, active worlds like Earth or Enceladus, we understand the mechanisms. Volcanism, tectonics, or cryovolcanic flows can repave the landscape, wiping the geological slate clean. But Methone is only about 3 miles across. It possesses such a minuscule amount of mass that its gravitational pull is almost negligible. This lack of gravity means it cannot generate the internal heat needed to power any kind of traditional geological activity. It should be a dead, frozen, and static relic, a museum of impacts from the last 4 billion years. Its surface should be utterly pulverized, a testament to the relentless bombardment of the space environment. The fact that it is not suggests that an entirely different set of rules governs the fate of small moons orbiting within a planet's ring system, a set of rules we are only beginning to decipher. The most compelling theory to explain this impossible smoothness points not to internal forces, but to a constant, gentle rain from above. Methone orbits within a faint arc of material that is itself part of the diffused G-ring. Scientists believe this moon is the likely source of that ring's dust, and in return, it is constantly being dusted by its own debris. The surface of Methone is likely covered in an incredibly fine powder, a layer of ultra-fine regolith that behaves less like solid ground and more like a fluid. In the microgravity environment of this tiny world, the electrostatic forces between individual dust grains can be stronger than the moon's own gravitational pull. This means that any impact, even from a tiny micrometeoroid, doesn't create a permanent crater. Instead, it would send ripples through this delicate dust layer, much like a pebble dropped into a pond, and the electrostatic cling would cause the material to slowly flow back in, smoothing over the blemish. It's a self-healing surface where the very forces that would make a landscape on a larger moon are completely subverted by the bizarre physics of the ultra-small. This leads to an even more fascinating possibility, that Methone is not a solid body at all, but a fragile assemblage of material known as a rubble pile. However, its perfectly smooth, egg-like shape suggests this rubble pile must be incredibly cohesive and uniform, held together by those same electrostatic forces that smooth its surface. This creates a delicate balance. The Moon is just strong enough to hold itself together under its own weak gravity, but its surface is so fragile that it cannot retain any record of its violent history. Every impact is a temporary event, its memory erased by the slow, oozing flow of dust. This would make Methane and its siblings, like the similarly smooth moons Pan and Iapetus, an entirely new class of object, not solid worlds, not loose rubble piles, but gravitational dust bunnies, whose form and existence are dictated by the invisible forces of static electricity and the constant, gentle drizzle of their own ring material. They are ephemeral worlds, their flawless surfaces a silent testament to the unseen, delicate forces that can shape the cosmos on the smallest of scales. This striking thermal asymmetry between Saturn's poles presents a puzzle that defies our basic expectations of planetary heating. Logic would suggest that two polar regions receiving roughly the same amount of sunlight over a full Saturnian year should exhibit similar temperatures. Yet, detailed measurements from the Cassini spacecraft revealed a persistent and significant imbalance, with the North Pole consistently registering as hundreds of degrees warmer than its southern counterpart. This disparity is not a minor fluctuation. It is a fundamental feature of Saturn's atmospheric structure that our current climate models struggle to reproduce, pointing to a complex and hidden energy redistribution system operating within the gas giant. The initial clues to this mystery emerged from the planet's profound seasonal cycle. A year on Saturn lasts nearly 30 Earth years, meaning each pole endures a decade and a half of continuous sunlight followed by an equally long period of darkness. As the Northern Hemisphere emerged from its long winter during the early phase of the Cassini mission, scientists anticipated a gradual warming. However, the rate and extent of that warming were startling. The North Pole not only heated up quickly but became and remained substantially hotter than the South, even after the Southern Hemisphere had its own summer. This persistence of the temperature gap across seasons suggests the imbalance is not merely a temporary effect of solar heating, but is instead baked into the planet's deeper atmospheric machinery, a constant discrepancy that sunlight modulates but does not erase. A primary suspect in this case is the planet's incredible auroral activity. Both poles host magnificent permanent auroral ovals, where charged particles from the solar wind funnel along magnetic field lines and slam into the upper atmosphere, depositing immense amounts of energy. This process acts like a giant polar heater. For a time, scientists believed differences in the intensity of these auroras could explain the temperature gap. However, further observation complicated this theory. While the auroras do inject tremendous heat, the energy input from them is remarkably similar at both poles. If they were the sole factor, the temperatures should be much more balanced. This indicates that the energy from the auroras is being handled differently by the two hemispheres. It's not about the amount of heat arriving, but about how that heat is then managed, trapped, or distributed within the unique atmospheric dynamics of each pole. The plot thickened with the discovery of a massive, persistent hurricane locked over Saturn's North Pole, nestled perfectly within the hexagonal jet stream. This storm, with its towering walls and clear eye, acts as a colossal atmospheric mixer, churning and trapping warm air. Scientists theorize this vortex creates a kind of self-contained thermal engine, efficiently retaining the heat generated by the northern auroras and preventing it from dissipating into the lower latitudes. The South Pole, by contrast, lacks a similar, long-lived polar vortex of the same strength and stability. Without this efficient containment system, heat deposited by the southern auroras may be more readily lost, radiated away into space, or transported elsewhere by winds, preventing the same level of intense warming. This difference in polar weather systems appears to be a critical key to understanding the thermal divide. Yet, even the combination of auroral heating and vortex dynamics may not tell the whole story. The sheer scale of the temperature difference hints at another, more subtle factor, a potential asymmetry in the planet's own internal heat flow. Saturn radiates more than twice the energy it receives from the Sun, a leftover warmth from its violent formation. It is possible that this internal energy is not rising uniformly from the planet's depths. Convective patterns or large-scale wave activity within the deep atmosphere could be channeling more of this primordial heat toward the northern hemisphere, providing a continuous background warmth that supplements the energy from the Sun and the auroras. This would mean the North Pole's warmth is not just an atmospheric phenomenon, but is fueled in part by a deeper planetary scale process that we cannot yet directly observe, a fundamental lopsidedness in the very way Saturn cools itself off. The enduring mystery of the polar temperature asymmetry is a powerful reminder that gas giants are not simple, symmetrical spheres. Their fluid interiors and complex atmospheres can sustain stable, long-term imbalances that challenge our Earth-centric views of how planetary systems operate. Unraveling this particular puzzle requires us to understand the intricate three-dimensional conversation between a planet's deep interior, its magnetic field, its global circulation, and the external driving force of the Sun. A conversation that, on Saturn, seems to have a distinct and persistent northern accent. Far beyond the orderly dance of Saturn's inner moons, in the cold, dark reaches of its gravitational influence, orbits a renegade that refuses to follow the rules. This is Phoebe, a world that moves to the beat of its own drum, quite literally spinning backwards around the planet compared to nearly every other significant moon in the system. This retrograde orbit is the first glaring clue that Phoebe is an outsider, an interloper that was not born in the Saturnian family but was captured from the deep freeze of the outer solar system. But its rebellious path is only the beginning of the story. When the Cassini spacecraft conducted a close flyby, it revealed a surface unlike any other in the region, dark as soot and pocked with deep craters that exposed bright, pristine ice beneath, a clear sign of water. Even more telling was its density, which was found to be significantly higher than the porous, icy moons native to Saturn. This combination of traits, a retrograde orbit, a dark, complex surface, and a rocky, icy composition, paints a compelling portrait of an object that formed not in the warm inner solar system, but in the distant realm beyond Neptune, in a region we call the Kuiper Belt. Phoebe, it seems, is a captured centaur, a primordial piece of the solar system's building material that was pulled into Saturn's service long ago. The central mystery, then, is not necessarily what Phoebe is, but how it came to be where it is. Gravitational capture is an exceptionally tricky cosmic maneuver. For a planet to capture a passing object, that object must lose a significant amount of its orbital energy, effectively slowing down enough to be snared by the planet's gravity without simply crashing into it. In the vast emptiness of space, there's no natural brake pedal. One prevailing theory suggests that Phoebe's capture was not a solitary event but a chaotic, multi-body interaction. In the early, violent days of the solar system, the region around the giant planets was likely swarming with countless small, icy bodies. The leading hypothesis is that young Phoebe may have been part of a binary pair, two objects orbiting each other. As this duo made a close pass to the infant Saturn, the planet's immense gravity could have torn the pair apart, absorbing the energy of one object to capture the other. It's a gravitational slingshot maneuver in reverse, where the energy lost by one body is used to bind the other to the planet. This elegant, if destructive, process would neatly solve the energy problem, providing a plausible mechanism for how this Kuiper Belt object could have been persuaded to stay. However, the mystery deepens when we consider the aftermath of such a violent capture. Being grabbed by a gas giant and wrenched into a new, tilted and backward orbit should be a traumatic experience, one that would likely shatter a loosely bound rubble pile or leave clear signs of extreme geological stress on a more solid body. Yet, Phoebe appears surprisingly intact. Its shape is roughly spherical, suggesting it has enough self-gravity to have pulled itself into a relaxed form, a state that implies it was never completely torn apart. This resilience is puzzling. If it was captured billions of years ago, why doesn't it show more obvious scars from that chaotic event? The answer may lie in its composition and internal strength. Phoebe's higher density suggests it contains a significant amount of rock mixed with its ice, making it a much sturdier and more cohesive world than the fragile, icy moons like Hyperion. It was simply tough enough to survive the ordeal of capture without completely disintegrating, a hardy survivor from the solar system's earliest days. Perhaps the most fascinating consequence of Phoebe's captured status is the role it plays as a puppet master, indirectly shaping the environment of the entire Saturnian system. The dark, dusty surface of Phoebe is constantly being bombarded by micrometeoroids, chipping away small particles of its dark material. These dust grains are then flung off into space, creating a vast ethereal ring of their own, a diffused disk of fine debris that follows Phoebe's inclined orbit. This faint ring is the source of the dark material that rains down on other moons, most famously painting the leading hemisphere of Iapetus in that striking black and white contrast. In this way, Phoebe's influence extends far beyond its own orbit. It is a silent artist using the dark pigments of its own surface to color the faces of other worlds, a permanent reminder of its chaotic journey and its lasting impact on the Saturnian family it joined so long ago. But this precise choreography is only possible because of a far stranger and more fundamental mystery. The entire system exists in a state of delicate gravitational balance. The two moons are almost exactly the same size and mass, a near twinness that is absolutely critical for their orbital swap to function so smoothly. If one were significantly larger than the other, their dance would destabilize, likely leading to a collision or the ejection of the smaller moon. This raises a profound and unanswered question. How did two moons of such remarkably similar size end up sharing the exact same orbital highway? Did they form together from a single larger body that broke apart? Or were they two separate objects that, through a billion-year game of gravitational pinball, somehow found this perfect equilibrium? Their synchronized existence is a cosmic coincidence that seems almost too perfect to be accidental, a puzzle of origin that sits at the heart of their dynamical mystery. Yet the most baffling aspect of their performance is not the dance itself, but its astonishingly clean result. As the moons swap places, their combined gravitational influence acts like a pair of celestial sheepdogs, herding ring particles with incredible efficiency. They don't just nudge particles away, they create a sharp, well-defined boundary, a stark edge between the brilliant ring material and the empty void of the gap. This is profoundly difficult to achieve. Gravitational interactions tend to be messy, often creating wavy, chaotic edges or faint, diffuse ringlets within a gap. The cleanness of the Janus/Epimetheus gap suggests their gravitational kicks are perfectly timed and tuned to eject any stray particles that wander into their domain, preventing any from settling into a stable orbit within the gap. It's a flawless, self-sustaining cleaning mechanism operating on a scale of tens of thousands of miles. But herein lies the final and perhaps most intriguing layer of the mystery. Despite knowing the dancers and the basic steps of their routine, our best computer simulations of this process still cannot perfectly replicate the pristine gap we observe. The models tend to predict a slightly messier, less defined edge than what Cassini's cameras revealed. This discrepancy is a clear signal that some subtle physics is still missing from our equations. It could be that the tiny moonlets and self-gravity wakes within the ring itself play a role, interacting with the shepherding moons in ways we haven't yet accounted for. Or perhaps the exchanges of momentum between the moons and the ring particles during their chaotic orbital swap involve a level of complexity that we are only beginning to grasp. This small but persistent gap between our models and reality serves as a quiet reminder that even when we think we understand the celestial mechanics at play, Saturn's rings always hold a little more secrets in reserve, their elegant simplicity belying a depth of physical wonder that we have yet to fully comprehend. But just when we think we've categorized every kind of world in Saturn's system, from the active to the inert, one of its largest moons delivers a stunning surprise that forces us to rewrite the textbooks. Rhea, the second largest Saturnian moon, appears at first glance to be the very definition of a dead, frozen world. It is a heavily cratered ball of ice and rock, a quiet relic from the solar system's violent past with no signs of the internal dynamism that powers Enceladus's geysers or cracks open Dione's surface. Its gravity is weak, its surface temperature is a bitterly cold -300 degrees Fahrenheit, and it lacks any significant internal heat source. By every conventional law of planetary science, Rhea should possess no atmosphere whatsoever. Any gases released from its surface would immediately be lost to the vacuum of space, their molecules quickly achieving escape velocity under the moon's feeble gravity. This is why the data from the Cassini spacecraft was so utterly shocking. During a close flyby in 2010, Cassini's instruments detected a very thin but very real envelope of gas clinging to Rhea. This wasn't just a temporary puff of dust, it was a stable, albeit incredibly tenuous atmosphere, and its composition was the most baffling part. It was primarily made up of oxygen and carbon dioxide. This was a monumental discovery. For the first time, a spacecraft had directly sampled a native oxygen atmosphere on another world, and it was orbiting Saturn of all places. The concentration is incredibly low, about 100,000 million times less dense than Earth's air, but its mere existence on such a cold, seemingly inert moon presented a first-class enigma. How could such a fragile atmosphere possibly form? And what mysterious process could be constantly replenishing it against the relentless drain of escape into space? The key to solving this puzzle lies not in biology or geology, but in chemistry driven by pure physics. Rhea's surface is a vast field of water ice. This ice is constantly under bombardment from charged particles trapped within Saturn's powerful magnetosphere. These high-energy particles, primarily ions and electrons, continuously slam into the surface ice. When they do, they break apart the water molecules in a process called radiolysis. This literally shatters H2O into its constituent atoms, hydrogen and oxygen. The lightweight hydrogen, once freed, is quickly lost to space due to Rhea's low gravity. The heavier oxygen atoms, however, have a harder time achieving escape velocity. They linger longer, bouncing along the surface and occasionally colliding with each other, eventually building up the extremely thin molecular oxygen atmosphere that Cassini detected. But this elegant explanation only answers half of the mystery. While radiolysis beautifully accounts for the presence of oxygen, it does nothing to explain the carbon dioxide that was found mingling with it. Carbon dioxide is not a natural component of water ice. Its presence implies another, completely separate source. One compelling theory suggests that the same radiation bombardment could be unlocking carbon dioxide that has been trapped within Rhea's ice for billions of years, ever since the moon first formed. Primordial ices can often contain impurities and other compounds frozen within their crystalline structure. As the energetic particles penetrate the surface, they could be breaking down these ancient, complex carbon-containing molecules and reforming them into simple carbon dioxide gas, which then seeps out to join the oxygen. Another possibility points to the steady rain of tiny, carbon-rich micrometeoroids that constantly dust all moons in the solar system. As these particles impact Rhea's surface, the tremendous energy of the collision could instantly convert their carbon content into carbon dioxide gas, providing a steady external source. The true wonder of Rhea's atmosphere, however, is not its formation but its persistence. This entire system exists in a state of incredibly delicate balance. The atmosphere is being continuously created by the bombardment of radiation, and it is being continuously destroyed as its molecules fly off into space. For the atmosphere to be detectable at all, these two processes must be in a near-perfect equilibrium. The radiation has to be breaking apart water molecules at exactly the right rate to replace the oxygen that is constantly being lost. This makes Rhea's wispy breath a real-time demonstration of cosmic chemistry, a temporary halo born from destruction and sustained by a relentless rain of energy. It is a powerful reminder that even on the coldest, most silent worlds, the invisible forces of physics are always at work, painting thin, ghostly atmospheres onto worlds we once thought were merely barren and dead. Moving from the ethereal breath of Rhea, we plunge back into the swirling, dynamic heart of Saturn itself, where the atmosphere orchestrates a different kind of mystery, one of rhythm and pattern on a planetary scale. If you were to look at a detailed global map of Saturn's mid-latitudes, you would notice something strangely orderly amidst the apparent chaos of its stormy bands. Here, the clouds don't just swirl at random, they arrange themselves into a series of alternating clear and cloudy regions with a striking, almost musical regularity. These are not the turbulent, convective storms of the equator or the geometric perfection of the polar hexagon, but something far more subtle. A persistent, repeating pattern of bright and dark bands that look like the grooves on a vinyl record, a periodic signature etched across thousands of miles of cloud tops. This phenomenon is a textbook example of a planetary-scale atmospheric wave, a standing wave pattern much like a note being held on a massive, gaseous instrument. The leading theory points to a type of wave known as a Rossby wave or planetary wave. These are slow-moving waves in the atmosphere that arise from the planet's rotation and the variation of the Coriolis effect with latitude, the same fundamental forces that guide jet streams on Earth. On Saturn, as these waves propagate through the atmosphere, they cause air to rise and sink in a regular, repeating pattern. Where the air rises, it cools, causing water ice clouds to condense and form brilliant white bands. Where the air sinks, it warms, preventing cloud formation and creating darker, clearer regions in the atmosphere. The result is this stunning, striped pattern of cloud and clear sky, a direct visualization of the planet's hidden atmospheric music. The true mystery, however, is not the existence of these waves themselves, but their staggering regularity and stability. The spacing between these bands is remarkably consistent, and the pattern itself can persist for years, even decades, with little change. This longevity is what baffles meteorologists. On Earth, our weather is famously chaotic and unpredictable. Even large-scale patterns are constantly shifting and evolving under the influence of continents, oceans, and solar heating. Saturn has no such complicating features. It is a uniform sphere of gas, yet its atmosphere can lock into these resonant patterns with a fidelity that our own world seems incapable of matching. This suggests an atmospheric circulation that is far more orderly and predictable in its fundamentals than we might expect for a turbulent gas giant, hinting at a deep, stable structure beneath the visible tempests. And this is where the mystery truly deepens through a compelling comparison with its sibling, Jupiter. Both planets are gas giants with similar compositions and energy budgets. Both possess strong jet streams and banded structures, and both exhibit these periodic wave patterns. But they look completely different. Jupiter's analogous waves manifest as small, intricate ripples and chevron patterns, often packed tightly together and looking more like a finely textured fabric. Saturn's version, by contrast, is bold and broad-stroked, with fewer, much wider bands that are spaced farther apart. This stark visual difference is a profound clue, telling us that despite their surface similarities, the inner workings of these two giants' atmospheres must be fundamentally different. The leading hypothesis for this divergence points squarely beneath the clouds to the hidden hand of water. Saturn's atmosphere is thought to contain a significantly higher proportion of water vapor than Jupiter's. Water is a powerful player in atmospheric dynamics. It is heavy, and when it condenses into clouds, it releases a tremendous amount of latent heat. This extra energy could be the key that unlocks the different behavior. Scientists propose that on Saturn, the massive storms we see, including the great white spots, are driven by the powerful release of this latent heat from water condensation deep within the atmosphere. These colossal convective events could be acting as the primary engine that excites the larger, more robust Rossby waves we see, setting the entire atmospheric layer ringing with a deeper, slower, more resonant frequency. Jupiter, with a comparatively drier atmosphere, may lack this powerful, deep-seated driver. Its wave patterns might be generated by shallower processes, by the interactions of different cloud layers, or by smaller storms, resulting in those higher frequency, more finely detailed ripples. In essence, the different periodic patterns are a direct readout of the two planets' very different meteorological hearts. Saturn's bold stripes are the signature of a world with a deep, water-driven weather system, where immense forces welling up from the abyss create planetary-scale rhythms. Jupiter's intricate filigree suggests a weather machine operating more in the shallows, a complex tapestry woven from threads of a different composition. This atmospheric dichotomy shows us that even planets born from the same cosmic nursery can grow up to have wildly different personalities, their hidden depths revealed by the subtle, rhythmic music of their clouds. And now, we conclude our journey with a mystery not about what is present at Saturn, but about what is conspicuously absent. We've explored colossal moons like Titan and Rhea, and marveled at the countless tiny moonlets and shepherd moons embedded within the rings. But between these extremes lies a profound and puzzling gap, a void in the moon-size distribution that has left planetary scientists scratching their heads. Where are all the intermediate-sized moons, this missing middle class of satellites, worlds that should logically exist between the giant spheres and the tiny specks, represents one of the most fundamental and overlooked mysteries in the entire Saturnian system, a silent clue to a violent and chaotic past. When we look at the architecture of other planetary systems, particularly that of Jupiter, we see a much more continuous range. Jupiter boasts 4 massive Galilean moons, but it also has a whole family of mid-sized worlds like Amalthea and Himalaya, filling in the size spectrum between the giants and the small irregular captures. At Saturn, that smooth gradient is broken. We have the big 7 Titan and the other round moons like Rhea, Iapetus and Dione, and then we have a dramatic drop-off. The next largest moons, like Hyperion or Phoebe, are dramatically smaller, more irregular, and often captured objects. There is a stunning lack of native, spherical moons in the several hundred-kilometer diameter range, a size category that should be plentiful if moon formation was a simple, hierarchical process of accretion. This gap isn't just a curiosity, it's a glaring anomaly that challenges our standard narratives of how planetary systems assemble themselves. Scientists have developed several compelling and quite dramatic theories to explain this great absence. The first and most violent idea is one of catastrophic collisional evolution. The early Saturnian system was likely a far more crowded and chaotic place than it is today, filled with dozens of large moon embryos orbiting much closer to the planet. In this scenario, the intermediate moons did indeed form, but they were not destined to last. Their orbits may have been unstable, leading to a series of apocalyptic collisions. Rather than gently merging to build even larger moons, these titanic impacts could have been so violent and energetic that they completely shattered the intermediate-sized bodies, grinding them down into the swarms of tiny moonlets and ring particles we see today. The majestic rings themselves could be the icy graveyard of one or more of these lost mid-sized worlds, their substance forever scattered, leaving behind only the largest survivors that managed to avoid this early period demolition derby. A second theory looks not to destruction, but to the unique and powerful influence of Titan. As by far the most massive moon, Titan's gravity would have exerted an overwhelming influence on the primordial disk of material from which Saturn's moons formed. Its immense pull could have acted like a gravitational vacuum, hoovering up most of the available building material within its orbital zone and starving any potential competitors out of existence. This would have prevented the accretion of any other sizable moons near it, effectively creating a monopoly on mass for Titan and leaving only smaller, more distant objects to form from the leftover scraps. This model paints a picture of a system dominated by a single giant from the very beginning, a celestial giant that shaped its entire neighborhood through its sheer gravitational dominance. A third possibility is more pragmatic, suggesting the gap might be at least partially an illusion, a detection limitation. The space around Saturn is vast and filled with fine ring material, making the discovery of faint, dark objects incredibly difficult. It is entirely possible that a population of mid-sized moons does exist, but they are either coated in very dark, non-reflective material that makes them hard to spot from Earth, or they orbit in paths that have simply kept them hidden from our telescopes and spacecraft so far. The recent surprise discovery of many small moons by the Cassini mission proves that we are still capable of finding new objects. Future, more powerful missions with dedicated instruments might yet find these missing middle children, resolving the mystery by simply looking harder. However, the weight of evidence currently leans towards a history of violence. The very existence of bizarre, porous moons like Hyperion supports the collisional model, as they look exactly like the shattered remnants of a much larger body that never fully reaccreted. The pristine, ice-rich composition of the main rings also points to the destruction of a sizable, icy moon, rather than the gentle accumulation of leftover primordial dust. The missing intermediate moons of Saturn stand as silent, ghostly evidence of a dramatic and tumultuous birth for the ringed planet's family, a forgotten chapter of cosmic chaos that left behind only the largest survivors and the finely ground dust of their obliterated siblings. It is a final, humbling reminder that the serene beauty we see today is merely the peaceful aftermath of a truly violent past. And so we arrive at the end of our journey, having ventured past 25 of the most captivating enigmas the ringed planet has to offer. From the geometric perfection of the North Polar hexagon to the chaotic tumble of Hyperion, from the hidden oceans of Enceladus to the missing methane of Titan, each mystery we've explored stands as a powerful testament to a single, humbling truth. For all our robotic explorers and towering telescopes, Saturn remains a world of profound and beautiful secrets. We have flown through its ice-filled skies, listened to its silent radio songs, and mapped its swirling storms. Yet with every answer uncovered, a dozen new questions have emerged, each more fascinating than the last. This is not a sign of failure, but a celebration of the universe's infinite complexity. Saturn is a gift that keeps on giving, a cosmic puzzle box designed to challenge our intellect and ignite our imagination for generations to come. What makes these mysteries so thrilling is that they are not dead ends, but rather invitations, beacons calling out to the next wave of scientists, engineers, and dreamers. Every unexplained hexagon, every missing moon, and every contradictory measurement represents a frontier of knowledge waiting to be crossed. They are the unfinished sentences in the story of our solar system, and it will be up to future missions, perhaps even generations not yet born, to provide the answers. The Cassini mission was a magnificent chapter, but it was not the final word. It was the key that unlocked the door, revealing a vast mansion of rooms we have only just begun to step inside. The real exploration, the true discovery, lies ahead. Now, we'd love to turn the question over to you. After hearing about these 25 incredible puzzles, which one captured your curiosity the most? Does the two-faced mystery of Iapetus keep you up at night? Or are you endlessly fascinated by the silent, ethereal breath of Rhea's oxygen atmosphere? Perhaps the sheer scale of the great white spot storms left you in awe, or the delicate dance of the propeller moonlets has you pondering the subtle forces that shape our universe. Let us know in the comments below. We are genuinely excited to hear which of Saturn's secrets you find most compelling. If this journey into the unknown has sparked your sense of wonder, just imagine what other cosmic mysteries are waiting to be uncovered. The universe is filled with enigmas, from the icy oceans of Europa to the violent storms of Neptune, and we are here to explore them all with you. Make sure you don't miss out on our next adventure into the depths of space by subscribing to the channel and hitting the notification bell. Thank you for joining us on this incredible voyage to Saturn, the jewel of our solar system, and a permanent reminder that wonder is the true engine